Hi everyone, welcome to this talk. I'm Chuanwei Ruan, currently working as the machine learning engineer at Instacart. In this talk, we'll be talking about how do we rerun grocery item with quality constraint at Instacart using a counterfactual modeling approach. So firstly, what is Instacart and what do we do? Founded approximately 9 years ago, Instacart is now a leader in the area of online grocery shopping at North America. Basically, we work with different retailers so that customer can just get the food they need from those retailers delivered to their homes. So that basically is 4 parts of the business model as order online, pick from store, transportation, and final delivery. So at Instacart, we use the term quality to describe the reliability of our service. Basically, we want to get all the items our customer ordered, finally pick up and deliver to them on time. However, this is tricky when the availability of item changes all the time. The item for which the customer placed order for might go out of stock even before our shopper picks them in the store, maybe a few minutes or few hours later. As Instacart does not own nor operate its own warehouses, we use the signal from our retailer partners sent to us, as well as the information we gathered from our shoppers. And we have a so-called availability estimation model, which basically try to predict the probability of an item being available at a specific location in the future, a future time point. We also have some replacement item recommendation models as a part of the reliability control. It basically tried to provide the potential substitution items. And it is good recommendation models, but it is still not a perfect experience when replacement is needed. We still want the odd item the customer bought ordered to have a high availability in the beginning so that we have a high reliability. To achieve this kind of quality control using the item ranking can be quite simple. One way of doing that is to do the simple filtering. Basically, the idea is that we can simply filter out the item with low availability score. And however, this simple filtering can be problematic, and it will become increasingly difficult to set a good threshold for the filtering. And because a lot of business metrics and engagement metrics can be highly sensitive to this one single threshold, or maybe a set of thresholds if we tune it really carefully. And even so, the customer also get confused by this hiding strategy because that they might be very familiar with the store they are shopping from, and they will be confused that saying like, I know this item is there, why I'm not able to find it at the Instacart. So that's a bad user experience. And also it seems like there's a trade-off between auto quality and customer engagement with simple filtering logics. And the idea is if we use a high threshold, we might be able to have more items to be found during pickup time. But that also means that we might fill out a lot of really good items in the beginning. Having a lower threshold has similar observations. That means it has maybe have higher engagement, but on the contrary, a lower font rate, which hurts our reliability. But however, instead of just filtering item out, what if we just adjust item ranking in a smart way? Maybe we can get the best of both worlds, such as we can improve the font weight without really sacrificing engagement. And that is possible. The key idea is if we can demote low availability items to lower positions, if there exist high availability items with similar relevance, and that will help us improve the auto quality without hurting other metrics. And we call this re-ranking as quality constraint item re-ranking. This is a specific example where users do search for the Chobani probiotic strawberry yogurt. This is quite a specific search. There's three types of response. One is we just use search ranker and we did not do nothing. Secondly, we can do the simple filtering. Thirdly, is that we might have some smart re-ranking strategy. The number shown here are the estimated availability score. So you can see if we do nothing, the user might just pick top one or top two result and not able to get the item in the end, very likely. But if we just do the simple filtering, for average user, they might be happy. But for some users who are very brand loyal, actually they'll be not happy about the results. Well, it's not a problem for the re-ranking strategy because it depends on the combination of the relevance and the availability. You may still purchase this one, but just with a banana flavor. And with 50% of being available, it's still a chance like to get the item delivered. And for the other customer who are really not brand loyal, you can just find the result in the top one results. That's where we can get the best of the two worlds. Well, reasoning about it is kind of easy, but the hard thing is actually how to have a mechanism to really evaluate different re-ranking models or re-ranking strategies. And that needs us to answer the key causal questions. That is, we need to predict how each user might react to the perturbed ranking. For different users, the same search query and the same set of items with known relevant score. Suppose we have a different re-ranking model or strategies. How will the conversion rate finally will change? And how will the final font rate change? Without answering those two questions, we'll not really have the confidence to put the changes we bring online, because very likely we'll be messing around with or will like really have a better relevance if we are not careful. But estimating these two things are not easy. Firstly, the key idea is that the key idea of demotion itself rely on some list dependent or context dependent effects. That means we're not really able to use the pointwise counterfactual of estimation frameworks. Secondly, the effects of demotion also depend on the customer. So the model has to be somewhat personalized. Some customer might not like the favorite item rank be demoted, while the others don't care. Finally, the font rate only depends on the item that is finally converted, and that is what we observed. But when we perturb the ranking, it is unknown to us which item will be finally picked up by the customers. That brings a lot of uncertainty as well. So as you can see, if we want to solve the three problems very rigorously, that is very challenging. But it's a very important question. We still want to have some answers. So what do we do? Instead, we built a very generic list-wise simulators. Basically, we want using these simulators to understand how the found rate and click-through rate might change. Should we alter the ranking results by demoting some items? And we train the machine models using the feedback collected from the simulators. Basically, there are two types of features. One type is more like a static, that's the user's features, the user embedding we have from other models, or maybe the context from that for that search query specifically. What is interesting is the pooling function we designed for the observed data. That is, we have a list of items to rank, and we have all the relevant and the estimated availability score in place. So whenever we have a new ranking, we will be able to compute the features such as the min, max, or min top relevance of top 5 result, and has always been dynamic because it's subject to the position we give to the item, which is subject to the re-ranking algorithm we use. And after all the translations, everything will be just vector valued features, and we put them everything into a machine learning model with the multi-objective predictions. So it can be like conversion, click-through rate, and also the one important factor is the found rate. And of course, that's optionally whether we want to use the found rate as part of the objective, or we actually compute that by combining the click-through conversions and the availability. And with this simulation tools, now we can actually have the feedback loop. Just for simplicity, let's assume we have some demotion strategy depends on some key, 1 or 2 key hyperparameters. We can just tune those hyperparameters even manually, but keep interacting with the simulators. And at each turn, we just change the rank of the items. And as you can see from this example and the last slides, we're always able to get the feedbacks from the simulations. The final questions we might have is, well, does it really work? And it does. We try it in 2 examples. But firstly, before we really put things in productions, we try to cross-validate the simulation study by the data we collected from our past A/B test, in which we try to tune the different hiding threshold from 25% to 55 to 80. And from this plot, we can see the estimations from this counterfactual estimation where we increase the hiding threshold from 25 to 80%. The estimation from the model is actually quite close to the empirical estimation we got from the true data collections. And after getting the confidence from this cross-validations, we tune a set of different ranking strategies we proposed, and we picked 2 of them, put into the online A/B test. And the results are quite good. Basically, we are able to improve the found rate and auto quality without sacrificing the conversion rate in a statistically significant way. So of course, this result, this model is some kind of simplistic, simple, but with this model, we are able to quickly iterate our ideas without relying on the A/B test too much. And we only use the A/B test as a final guardrail of our ideas. And it really helps us to accelerate a lot of our experimentations without wasting money.